Hi, this is Ethan Nowoski with the Week 9 explainer video for Chapter 21, Question 74. The wording of the question itself is kind of long, so I'm not going to go too in-depth on the wording, but you can read it yourself if you want to pause it. But what it's asking us is it's presenting us with a diesel cycle, which, as they say, is similar to an Otto cycle. And they're giving us some values and some conditions for this diesel cycle. And they give us a figured, a pressure versus volume diagram to go along with it. And from the values they give us and the diagram itself, they're wanting us to find the pressure, volume, and temperature at each of the points of this cycle. So here's the figure itself that we're going to be looking at right here. And so we see that it starts at point 1. It does an adiabatic process to point 2. The heat is introduced from 2 to 3. And then from 3 to 4, we have another adiabatic process. And then we have an isochoric process from 4 to 1, completing the cycle. And in that 4 to 1 is when some heat is also leaving. So the values themselves that they give us the heat that's being added into the system, which is 1,000 joules. They give us the gamma of the function of the air, which is 1.4, the change in volume, so Vmax minus Vmin, which is 1,000 centimeters cubed, and I'm going to convert this to 1,000 times 10 to the negative 6 meters cubed, because that's what we're going to be using for this problem. We have the Vmax over Vmin, which is R is equal to 21. The temperature at point 1 is 25 degrees Celsius. Converting this to Kelvin, we have 298.15 degrees Kelvin. And they have us the pressure at point 1 is 1 atmospheric pressure. So they want us to present the information in a chart like this, and if we plug in the information that we do know, we can actually see that we already fill out part of the graph, but we need to fill in some blanks. So they give us all of the parts, all of the values for point 1, which is 1 atmospheric pressure, 1,050 times 10 to the negative 6 meters cubed, and 298.15 degrees Kelvin. They give us the volume at point 2, which is 50 times 10 to the negative 6 meters cubed. And then back again at point 4, we can see that the volume is the same. So again, it's 1,050 times 10 to the negative 6 meters cubed. And so we need to find the rest of the values. And so what we're going to do is, first, before anything, because this is a pressure problem, it's good to note some other parts of the system. And we know that the number of moles in the system is staying constant throughout, so we can actually calculate for the n using the values that they gave us for point 1. And if we plug all of those in, convert atmospheric pressure to pascals, we get that our number of moles is 0.429, and that's going to come in handy later on when we're trying to solve some equations. So then let's look at the process from step 1 to from point 1 to point 2. And as I said before, this is an adiabatic process, meaning that no heat is being introduced to the system. But that doesn't mean that the temperature isn't changing. The temperature is actually going to be changing significantly, as you're going to see. So will the pressure. And so what we're going to do is, because this is an adiabatic process, it's also an isentropic compression, meaning that it kind of goes hand in hand with the adiabatic process, and no heat being added or taken out because it's going so fast that the system is being compressed, the volume is being decreased, the pressure is being increased, and the temperature is also being increased. So this relationship gives us this equation from the book, which is temperature at point 2 over temperature of time point 1 is equal to volume of 1 over volume of 2, and this is all raised to gamma minus 1. If we actually solve for that, we see that the temperature at point 2 increased dramatically to 1007.68 degrees Kelvin. And if we use that value to continue on, we can use another slightly different, well, this is the same equation, but with different values for an ideal gas law, using pressure at point 2, which we're going to try to find, volume at point 2, and temperature at point 2, and we're going to try to find pressure. And we find that pressure at point 2 is this very large number, which is just about 71 atmospheric pressures. So that's all of point 2 kind of filled out. So we're going to look at the process from 2 to 3. So if we go back to our graph, we can see that the pressure isn't changing from 2 to 3, but heat is being introduced. So we have an isobaric situation process, and we're adding heat, QH. So this is where that value of QH is going to come in handy. So we're saying the pressure remains the same, so P2 is equal to P3, and that the volume of 2 over T2 is equal to volume of 3 over T3, and this is just relates to the pressure. And so to find the temperature at this point, we're going to use the change in thermal energy equation, which is the change in temperature, so the MCAT, and this is why we actually wanted to find that our number of moles was that. So we plug in our heat and our other values, and we actually solve that the temperature at point 3 is 1,801.33 degrees Kelvin. Using that value of temperature 3, we can call into this equation up here and solve for the volume at point 3 is 89.38 times 10 to the negative 6 meters cubed. So that's part 3, or point 3 all filled out. And we're going to just do a very similar to, from 1 to 2 is very similar to 3 to 4, because it's another adiabatic process. Instead, it's an isoentropic expansion this time because the volume is increasing. So in response to this, the temperature will decrease, and so will the pressure. So we have the same relationship of T3 over T4 is equal to volume 4 over volume 3, and gamma minus 1. Solve for T4, we get that value, so 672.14 degrees Kelvin. And then using that value for temperature, we can plug it back into our ideal gas equation and solve for pressure at point 4, which is about 2.25 atmospheric pressure right there. And so as you can see, it's exactly as we predicted. The temperature decreased, the pressure decreased, and the volume increased. So we can actually fill out our chart right here with all the values that we needed, and that's how we find the pressure, volume, and temperature at each of the 4 points of this diesel cycle. Thank you.